Good morning, everyone. Good morning. On behalf of my co-chair, Erdal Erkan, and myself, I'd like to welcome you to Istanbul. It's a great pleasure to see many friends, colleagues, as well as new faces. In the weeks leading to the conference, as you're well aware of, our organizing committee, in particular Erdal, IT Society President Gerhard Kramer, and myself, exchanged numerous emails and answered many inquiries as Istanbul, in particular Taksim Square, became the scene to the largest protests in recent history of Turkey. Luckily, it's much calmer and events are much more contained now, and we're very happy to be hosting the first ISIT in Turkey. I especially would like to acknowledge Erdal, whose web postings at the conference site ensured that all participants were up to date about the state of events here in Istanbul. Right now, the city is quite safe, but I would still like to remind you to exercise caution as you travel in and around Times Square and avoid large public gatherings. So we started yesterday with a full day of pre-conference tutorials and a welcome reception, and we have 4.5 days ahead of us, packed with 4 plenaries, the Shannon Lecture by the first woman Shannon awardee, Katalin Marton, 9 parallel sessions, student outreach and with its events, the awards luncheon, and the banquet. So I very much hope you'll be able to take advantage of this fantastic program while you also get to enjoy what the amazing city of Istanbul has to offer. So without further ado, I'm going to leave the floor to the technical co-chair, Amos Lapitot, who's going to introduce the first plenary speaker, Emmanuel Candes. Thank you.
Thank you, Elsa. My name is Amos Lapitot, and I had the honor, the privilege, and the pleasure of being a co-chair of the Technical Program Committee. Well, okay, at least the honor and the privilege. And my privilege now is to introduce to you our first plenary speaker. One of the things that co-chairs do is actually they organize the plenary talks, and the trick there is to try to start very, very early. And in that way, you can actually capture some of the best speakers, and we've been very fortunate to have done that. And you will see that this program this week is packed with superstar speakers. I will start by introducing Emmanuel Candes. I won't tell you all the awards and the prizes that he's gotten because we only have 55 minutes. So I'm going to try to keep it short. Emmanuel is a professor of mathematics and statistics at Stanford University, and also by courtesy, professor of electrical engineering at Stanford. He's very famous for his work on wavelets, or their extensions to curvelets and ridgelets. He's done a lot of work and pioneering work in compressed sensing, matrix completion, and he's also very famous for his work on numerical solution of wave propagation equations. I'm going to mention here just a few of his achievements, one of which was recently he was awarded the Poya Prize together with Terence Tao for his work on compressed sensing and matrix completion. He has received the Kolatz Prize for his work on wave propagation, compressive sensing, and some of the extensions of the notions of wavelets. And I think probably what may have been his first award could have been for his PhD thesis, which was the Popov Prize that he received in 2001. And also, as you've seen in the program, he is a receiver of the Waterman, the very prestigious Waterman Award, which he received for achievements of people under the age of 35. What can I say? We're delighted to have him. It's a real honor for us. And he writes in his biography that he has given over 50 plenary lectures at major international conferences, and now I call on him to give the jewel in his crown. Thank you.
Okay, good morning. Yeah, it's true I've given a lot of plenary lectures, but for some reason this one, I'm a bit terrorized. Okay, so I'm very pleased to, and honored to be speaking at ISIT this year, and would like to thank the program committee for inviting me. And in truth, I don't know much finer company than the IT Society and more beautiful cities than Istanbul, so this should be a fantastic week, provided we agree that the week starts at 9:30 right after this lecture. So the topic of this lecture is the effectiveness of convex programming in the information sciences, and I do not have the skills or the competence to actually present a grand theory or a grand view of the interplay between these two disciplines. So what I'm going to do today is I want to talk to you about 3 stories from my own recent work. And so to quote from someone famous, 3 stories, that's it, no big deal. These stories have all in common a theme, which is that information about an object of interest may be missing. And so in the first story, we're going to see that we're going to miss the phase of an optical wave. In the second, we're going to miss many entries of a data matrix of interest. And in the third, we're going to miss the high-frequency spectrum of a high-frequency object, possibly a signal or an image of interest. Now, in all these cases, recovery is challenging, yet we will see that simple formulations based on convex programming are able to recover missing information as soon as information is recoverable by any method whatsoever. And so I shall begin with my first story, which is about phase retrieval, and its joint work with, or the fruit of my collaboration with the researchers that I've listed here. So phase retrieval is a century-old problem that has its origin in X-ray crystallography. And as I'm sure everybody knows, X-ray crystallography is a method for determining the structure of a crystal. And the way it works, as I'm sure you know, is that you have a source of X-rays of collimated beams that you strike onto a crystal. Then these rays get diffracted and you collect the diffraction pattern. Okay, so out of this image that you're making, so you have this beam of X-rays, you collimate them, you strike the crystal, they get diffracted, you get an image, and out of this image you would like to recover the 3D structure of the crystal. Now this is an important area of science, obviously. I did a rough count of the Nobel Prizes in chemistry and physics, and I count 10 Nobel Prizes in this area alone. Now, of course, the importance has to do with things like this, the discovery of the double helix structure, which was made possible by exquisite X-ray photographs taken by Rosalind Franklin in the early 50s. And I would like to say that this is perhaps the most significant scientific discovery since World War II, but since this is ISIT, I'm going to change it and I'm going to put since 1948. Okay, so the missing phase problem has to do with the fact that many times in life we have to deal with the fact that detectors can only measure the magnitude of diffracted rays, the magnitude of optical waves. They cannot measure phase information. And so when you, in X-ray experiments, when you strike crystal with a beam of light, because the wavelength is so short, you can only measure the intensity of the electrical field. Now, because the wavelength is short, you're almost immediately in the far field, and so the laws of physics tell you that essentially the electrical field is simply the Fourier transform of your crystal. And so an X-ray experiment is essentially measuring the modulus of the Fourier transform of a signal of interest. Right? So you would like to see the Fourier transform, but you don't. You just see its magnitude. And what is a phase retrieval problem? It's the following inversion problem. Is given that I only see the magnitude of the Fourier transform, how can I recover the phase? Okay. So I know that the phase carries a lot of information about a signal of interest, and probably you know too, but let's check this on a simple experiment. Here we've got 2 gentlemen, the 43rd and 44th President of the United States, and what I've done is I've computed the Fourier transform, which is something that looks like here. And now I'm going to keep their magnitude but swap their phase. Okay, a very simple experiment. I'm going to keep the magnitude but swap the phase. Right, so the magnitude I'm going to keep, I'm going to put the phase of this guy here, the phase of this guy here, but the magnitude is the same. And then I invert the Fourier transform. And when you do this, you get something like this, which every physicist and hopefully every electrical engineer knows, that most of the information in a signal is carried by the phase, not by the magnitude. Okay, so what's exciting about phase retrieval and phase-less measurements is that they were all the rage in the early, and well, as I said, in the 20th century. This is the first X-ray photograph ever taken by Röntgen. It's a hand of his wife wearing a wedding band, first Nobel Prize for physics. And now what's exciting about X-ray imaging is that people are trying to do very fancy things with X-rays. And for example, at SLAC, researchers, SLAC is a Stanford Linear Accelerated Center, people are trying to use X-ray diffusion imaging, X-ray imaging, to actually image large protein complexes. The way it works in a nutshell is that you have these large protein complexes. They're going to be dropped in front of a high energy laser that is going to illuminate them with very high intensity, and you collect a diffraction pattern just before the molecule explodes. Okay, so you have ultra-short X-rays, you collect a lot of diffraction patterns, and then you would like to recover the 3D structure, something as messy as this thing. And as I said, it's a very exciting area of science at the moment that makes the cover of many prestigious magazines. Okay, so what is the problem that we're trying to solve? What is a phase retrieval problem? Mathematically, if we set it up in discrete time, it's a very simple problem. So I'm going to take a discrete time approach where we have a signal x naught. So this could be the pixel of the image we wish to form, for example, the pixel values. They're complex values, right? It's an optical wave. This is typically the Fourier transform of something of interest. And so I would like to make linear measurements about this x, but I can't. I can only measure the magnitude squared. And so I've got quadratic equations about this object x naught. Okay, so I don't get to see the sign of this equation, the phase of these equations. So phase retrieval is a following feasibility problem, is given some measurement b, find an x which is compatible with this quadratic equation. So solve this quadratic system. Now, it's well known in complexity theory that if you could do this in polynomial time, you could advance complexity a great deal. Okay, in fact, this problem is NP hard in general. Yet, of course, it's extremely important to be able to solve the phase retrieval problem, so people have devised algorithm for doing so. And there was a time where if you had a good idea, you might actually get a Nobel Prize. That's what happened to Hauptmann and Carly, who made very specific use of the signal they were interested in, typically that you have a very sparse signal. They made specific prior of this knowledge to define an algorithm, a Bayes-like algorithm, and were awarded the Nobel Prize for chemistry in '85. Their method is not so much used anymore. What's used is really the standard approach, which is the Gershberg-Saxton algorithm or the finite algorithm, which is an iterative algorithm that I'm not going to describe because of time constraints. And what this algorithm does is you take a guess, you project it into data space to be consistent with the modulus. Then you get a guess, you project it back into space, you project it onto some a priori notion of what the signal should be, and you alternate like this. And this algorithm is very ad hoc. Sometimes it works, and sometimes it does not. Okay, so this lecture is about convex programming. And so what we're going to do is we're going to cast a phase retrieval problem as a convex program, even though it is extraordinarily non-convex. Solving quadratic equation is as far as a convex program that I can think of. So this is our problem. We want to solve these quadratic equations. And we're going to use a lifting technique, which is as follows, which is very, very simple. What I'm going to do is I'm going to introduce a matrix variable, capital X, which is XX star. And then I'm going to think about the measurement, the quadratic measurement, in terms of capital X. All right, so now I look at my quadratic measurement. This is the squared modulus of ak dot x. And I'm going to write this in a suggestive form as saying, well, this is a trace of a scalar. And what is this scalar? Is x dot ak times ak dot x. Right? That's the squared modulus of ak dot x. And then I'm going to switch this term around. And so I see the trace of ak stars, xx stars. I'm going to give name to these things. So let's call the matrix AK the rank 1 matrix AK star. And so what this is doing is really turning quadratic measurements about little x into linear measurements about capital X. All right, so now I don't have linear equations, quadratic equations now, I have linear equations. And so I can think about the phase recovery problem as the following problem. What I need to do is I need to find a matrix X which is compatible with the measurements I've just taken, the outcome of these X-ray experiments. And this matrix capital X needs to be positive semidefinite and rank 1 because it is XX star. Okay, so another way to see this is, well, there is a rank 1 solution, and the rank 1 solution is a truth, XX star. And so what we have is equivalent to finding a matrix with minimum rank. Here, rank would be 1 at the optimal solution, which is compatible with the measurement and is positive semidefinite. Now, when I do something like this, of course, I don't do anything. I just look at the problem slightly differently. And the problem is still combinatorially hard because of the rank constraint, which I cannot deal with in practice. So the next step is to remove the stuff we can't deal with here and replace the rank functional, which is simply counting the number of non-zero eigenvalues by something which is tractable. And we're going to use a convex proxy for this, which happens to be the trace. So phase lift is the relaxation problem, where we're going to try to solve the phase retrieval problem by semi-definite programming, by finding a matrix has a minimum trace and is compatible with the measurements that I have taken. Right? As you can see, this is a very simple formulation. This is a semi-definite program, and all I'm doing is I'm taking the non-convex phase retrieval problem, which we see here, and just replace the rank functional by its proxy, its convex surrogate, namely the trace. Right, so again, I'm going to repeat myself. The rank is simply counting the number of non-zero eigenvalues. The trace is summing them up, so the trace is to the rank what the L1 norm is to the L0 norm. Now, do we have people who don't know what is semi-definite programming? Well, I knew this was a fantastic audience. So you can skip the next slide. All right, so semi-definite programming is a very friendly class of convex optimization problem for which we have efficient software, theory, and algorithms. And so when you see something like this, this is something you can think about solving on a digital computer. Okay. All right, so we're doing something a bit bizarre here, because we start with quadratic equation, and of course we will need more quadratic equation than there are unknowns. So we start with an overdetermined system in which we have more quadratic equations than unknowns. And then we lift it up, but then we do something which is unthinkable, that now we had an overdetermined system, and now we create a highly underdetermined system. So if you imagine that you have on the order of n equations, all of a sudden now, well, how many unknowns do we have in this problem? Well, n squared. How many equations I have? Well, still on the order of n, and so we are extraordinarily highly underdetermined all of a sudden. Okay, so this idea of relaxing quadratic programs into convex forms is not really new. It was proposed by Shor for polynomial optimization as early as 1987, and perhaps most of you in the audience know that this was really made very popular by Gummins and Williamson in the seminal work, where they showed an approximate relaxation of max cut using semi-definite programming ideas. Now, if you want to know more about these lifting techniques, we're using a non-standard lift here. I encourage you to read this beautiful monograph by Bental and Nemirovsky, where they dedicate a few hundred pages to this topic. In phase retrieval, what's surprising is that this had never been considered, even though my colleague George Papanikolaou at Stanford proposed a similar approach at about the same time for array imaging. Okay, so what we're trying to do here is we're trying to suggest to use semi-definite programming to actually recover signals from phaseless measurements. So to show you the complexity of the phase retrieval problem, because you do not get to see the signs of those equations, only their magnitude, whenever you take a measurement, let's say you're real valued, then you would not know whether the sign is plus or minus 1, so you would not be able to know whether the solution is on this plane or on this plane. When you see the sign, of course, you disambiguate the two. So each time you have an ambiguity. And now you're going to take more and more measurement, more and more data, And so you start taking more and more measurements, right? And so the number of measurements increases. Okay, and so at the end of this acquisition process, what you know is you have this polytope, which is the intersection of all these pairs of planes. And you know that a vertex is solution, but you have no idea which one, and the problem is there are exponentially many, and nobody knows anything better than brute force searching. Now, if you have complex data, it's worse because, of course, now you don't have pairs of planes. When you only see the magnitude of a complex number, it's not that you are on this plane or on this plane. You're on an algebraic surface now, and so now you have a very delicate problem in algebraic geometry where you need to find the intersection of algebraic surfaces, and this is a very hard problem. Okay, all right, so what can we do? Well, we're going to see that, surprisingly, this strategy works. So we have our quadratic equations, which are like this. We're going to solve them by this phase lift approach, by this semi-definite program. And to state a mathematical statement, I'm going to assume that I'm giving you randomized equations, a bit in the spirit of compressed sensing. So I'm going to assume that the quadratic equation you'll see are kind of random, where the AKs are going to be vectors that are sampled on the unit sphere. And that sphere will be real if you're looking for a real signal, or complex if you're looking for a complex signal. Okay? And the main result of story one is this, is that if I make a number of quadratic measurements, which is proportional to the number of unknowns, so let's say 10 times n or something like that, then something really bizarre occurs, that is, with very high probability, that is, with a probability of failure which is exponentially small in the number of quadratic measurements. When I solve the semi-definite program, in fact, I don't need to solve a program, I need only to solve a feasibility problem. I'm trying to look at a matrix which is compatible with a measurement and positive semi-definite. When I look at this feasible set, it's only one point, which is xx star. So by just solving a feasibility problem, I recover xx star. There's only one guy in this feasibility problem. And so if I know xx star, I factor it, and I get x up to global phase. All right, so again, what happens is I make a number of quadratic measurements which is simply proportional to the number of pixels or pieces of information in your signal. I solve a feasibility problem. I just find a point which is in this affine space, which is compatible with this measurement and positive semi-definite. There is only one such guy, and it's the guy I'm looking for. Now we know from work in algebraic geometry, of editing and so on, that to have a well-posed problems, we need a number of equations which is at least 4 times n in the complex case. And what that says is, of course, is if you're a little bit above 4 times n, this will solve it exactly. Now this is a bit bizarre, and when you run experiments, what you do is, for those of you familiar with compressed sensing, you see a very sharp phase transition. If you take something like 6n measurements and above, this always works. And if you take a little bit below, then it fails. Right? So you have a very sharp transition between the regime in which it works and which it fails. And when you solve this on the computer, you know, from something like 5n measurements, whether I give an input signal, which is a low-pass signal, or random signal, it doesn't matter. The theory is blind to the structure of x. It recovers any x whatsoever. And so what we see in practice again and again and again is that from essentially 5n quadratic equations, this method will always return the truth. Now, how is this possible? How can this set contain a unique point? Because this is a bit bizarre. If you plot the positive semi-definite cone, and here you see the limit of my abilities, the semi-definite cone, so here is in 2 dimensions, I'm looking at matrices parameterized by 3 numbers, x, y, z, positive semi-definite. The positive semi-definite cone is everything inside this kind of parabolic shape. It's a very fat body, a bit like me. And now you slice it by an affine space, which is of enormous dimension. And what the theorem says is that there's only one point in the intersection. How can it be when everybody can see that there's an enormous number of points in there? Well, I know this is a savant audience, so people will say, hey, wait a minute, Emmanuel, the low-rank matrices are on the shell of this positive semidefinite cone. They are extreme points of the PSD cone. And so if there are extreme points, like they're on this shell, so maybe now when I even have a high-dimensional subspace, I can still maintain tangent condition. Okay, and so this is what happens, but, well, how come that even if this space is enormous, I'm still tangent? And the reason this works, I cannot, of course, prove it in this lecture. I mean, something I can prove, but do I really understand it? And I'm going to tell you the way I understand this. Is that you're looking for a rank 1 matrix, XX star. So you take a rank 1 matrix, and let's try to perturb it by adding a symmetric matrix, H. But no matter how I perturb it, because I have one eigenvalue which is positive and all the others 0, when I add a symmetric matrix to it, it's not going to be positive semidefinite. Some eigenvalues are going to be negative. So I take a rank 1 matrix, I perturb it, well, it's not positive semidefinite. Take another perturbation, for the same reason it's not positive semidefinite. I take a third, well, you guessed it, it's not positive semidefinite. So what are those directions that maintain positive semidefiniteness? They're very, very few, and they're very, very narrow. And so what that means is that the cone of positive semidefinite matrices around XX star looks something like this. And it's extremely narrow. And so now you take very few measurements, so you have an affine space of enormous dimension, but it doesn't matter because this cone is so pointy that it will become tangent. And there's only one point in the intersection. So you see that you can move this thing around and still have only one point in the intersection. Okay. All right, so now you can extend this to when you have noise, and that's the beauty of convex modeling. If I have noise, what you do is now I have measurements which are not exactly quadratic, but they're distributed about these quadratic measurements. What you do is, well, I'm not going to enforce AX equals B. I'm going to do some kind of least squares fit by minimizing some kind of residual sum of squares. And when you do this, you can show that you are at the information theoretic limit, that you get a mean squared error, which is not improvable in some sense. Okay, and that explains why this method works well in practice. What this noisy theory explains is that you have very smooth, nice degradation of mean squared error as the SNR decreases, and then it predicts very well the curve that you get to see when you apply this in practice, where you see this kind of SNR curve that you would get if you were to solve a least squares problem or something like this. All right, and so you can apply this for images and recover complex images from quadratic measurements, and we've done it. And so this has, of course, it's a new method for actually solving the phase retrieval problem that comes with, of course, lots of applications. Okay, so this was my first story. Okay, so the recovery of signals, even though we have phaseless measurements. My second story might be more familiar to you, so we may consider this to be an interlude. It has to do with robust principal component analysis, which is joint work with a new set of collaborators that I've listed here, and Emma and John Wright are wonderful people working in computer vision. All right, so now we're going to look at a different problem, and again, we're going to see that convex programming is surprisingly effective, and the problem is something like this. I've got a data matrix, which I can observe. We're going to call this data matrix M. And this data matrix is a superposition of a low-rank matrix, which we're going to call S, and a sparse low-rank matrix, which we're going to call L, and a sparse matrix, which we're going to call S. And the data matrix is observed, but the low-rank and sparse component are not observed. And your goal is, well, given the sum of L and S, can you recover the low-rank and sparse components accurately? Again, we have missing information because it's the same problem as having two numbers A and B. I show you their sum, and you see 3, and I'm asking you what is A and what is B. Right? So we have a blind or a blind deconvolution problem, if you will. This problem was also considered in a very beautiful paper by Chandrasekaran, Perillo, Shangavi, and Wilski. So why do we care about problems like this? We care about this because of principal component analysis. So in principal component analysis, as everybody knows, it's a technique for dimensionality reduction that works something like this. We've got a matrix like this, and so we have points in d dimensions. So this is the first point, the second point, the third point, and so on and so forth. And we think that these points are around a low-dimensional structure. And so I've plotted this as follows. Well, I can only plot in 2D, so the first point is here, the second point is here, the third point is here, and so on and so forth. And so indeed, they're around a low-dimensional structure, a line. But suppose that in this matrix, an entry has been incorrectly entered. So in fact, these points were like this, but because perhaps of a sensor failure, this entry used to be something, but it's been changed. Now, geometrically, what happens is that the other points are still at the same place, but these points, which used to be here, is now here. And now you run principal component. So you find the direction of principal variance, and you would find this red line. And that has nothing to do with what we're looking for here. And so what we notice on this very simple example is if I have one corruption in this matrix, then PCA may completely break down. This is something we don't really teach our undergraduates. Now, this is problematic because in this big world of big data, where data gets increasingly dimensional, we cannot possibly ignore the fact that not all data points are reliable. In fact, if you're working on image processing, you're going to have occlusions, which are going to mess up principal components. If you're working in bioinformatics, you're going to have sensor failures. If you're working with web data, you cannot ignore the fact that users may tamper with your measurements and your data. And so in all of these applications, if you want to extract meaningful information, if you want to reduce dimension in a meaningful way, you're going to have to make sure that your technique is robust to these possibly adversarial errors. Okay, so I got interested in this because of the Netflix prize. In the Netflix prize, as everybody knows, we've got a data matrix in which the rows are users and the columns are movies. And this is a separation problem which is compounded by the fact that not only we have corruptions, but we have a lot of missingness as well. And so in the Netflix matrix, we observe samples of a low-rank matrix, which are the true users' preferences for movies. And why is it low rank? It's because, well, people's preference tend to depend upon only a few factors. But in the Netflix data sets, I've been told, you have data points, that is, you have users' ratings that are completely bogus, users' input ratings purposely wrong, and so you cannot ignore this fact. So what you see is you get to see samples of a low-rank matrix, or approximately low-rank matrix, contaminated by impulsive noise. Okay, and the goal is to kind of recover the low-rank structure to be able to guess users' ratings for movies they have not yet seen. Okay, so we've got this model in which we have information about a matrix which naturally decomposes itself as a low-rank plus sparse component. We may also have a lot of missing entries. And so here we've got entries that are corrupted. Of course, we don't know which one they are a priori. We have entries that might be missing. And so this occurs in lots of problems in data analysis. And now this L plus S model, this way of looking at the world as a low-rank plus sparse component, has gained traction in a lot of other communities. For example, there's again this very beautiful work of Chandrasekaran, Shankavi, Parillo, and Wilski on graphical modeling with hidden variables, where they introduce this low-rank plus sparse decomposition in a very natural fashion. And I will just mention some ongoing work in dynamic MR, where this model is gaining a lot of traction. And if I can get... Right, so in dynamic MR, you've got a situation that looks like this, where you're trying to speed up MR, but now you do it not one image at a time. Now you're interested in actually a full video sequence. And what you can think about when you have a video sequence of MR images is that, well, there's a static background. So if I think about each image as a column in a data matrix, there's a static background. and this is going to be a low-rank component. But of course, things are moving, and so there's a sparse innovation on top of the static background. And so what the L plus S model is very useful is actually very good at recovering the state-of-the-art videos, the highest resolution video we know how to produce based on undersampled MR measurements. Now with these colleagues from NYU, Ricardo Tasso and Daniel Sodikson, we've used this L plus S model in the context of dynamic MR. And a particular application is MR angiography, where the sparse components reveals exquisitely the blood flow within the vein, so it does background subtraction, if you will, so that you can focus attention on the relevant part of the video. Okay, so this model is being applied. It's been applied in computer vision, it's been applied in MR, and it's been applied in many other fields. Okay, so now I want to perform this separation. Now you give me the sum of a low-rank matrix and a sparse matrix, and I want to perform this separation. And so, of course, this problem has to make sense. So if you give me a low-rank component which looks like this, and you just say, well, Emmanuel, this is your data matrix. What's a low-rank component? What's a sparse component? Well, this problem makes no sense because you make matrix which is both low-rank and sparse, so I would not know. I cannot disentangle them. Right? Because you give me a matrix which is both low-rank and sparse. How would I know which is which? And conversely, if you give me a sparse component, well, it cannot be low-rank. So in particular, if you give me a matrix that looks like this, well, is this a low-rank matrix? Is this a sparse matrix? Well, it's both. So how can I solve this problem? Now let me go back to the meaning of this. What we don't want to see. We don't want to have a low-rank component that is sparse, and conversely, a sparse component that is low-rank. And explain me, going back to this Netflix price problem, let me explain what it means. Suppose in the Netflix data matrix I have two users, and they're completely different from everybody else. They have preferences that have nothing to do with the rest of the world. Okay, and here they are. And in fact, they might be the same users. They may be perfectly correlated, for all I know. Suppose that these two users have decided to enter bogus ratings for The Godfather, which is here. How would I know whether they like The Godfather or not? I can't. I would be able to do this if I had users with similar preferences that I can use to actually detect that their entry is bogus and correct it. And so when we have a matrix that looks like this, a low-rank matrix that looks like this, then you can corrupt it in such a way that, of course, information is lost forever. Because what I need to corrupt this information, I need rows that look like this, that are correlated with these rows, so that I can detect that this is a corruption and correct it. I need to use the experience of other users. All right, so we cannot have sparse low-rank matrices in one condition, which we found useful with Ben Resch early on work on matrix completion, would be to say, well, I don't know how to say it in a few words, but I would say, when I look at this matrix, it's not sparse, or a way to say this geometrically is that the column space and the row space of the matrix cannot be aligned with the coordinate axis. Okay, so let's say we have an incoherent matrix, something like this, a beautiful spread out matrix which is not sparse, something that looks like this. And of course, this is a rank 1 matrix, so this is a very easy object according to our theory. And again, as we've seen, if I attack it by corrupting it in a very organized fashion where I delete everything that is in the first column, how would I ever know what is x1? I will never know. So for this reason, we're going to assume in the second story that, well, you can corrupt these entries, but the entries you're going to corrupt are going to be selected at random. And then you can do everything you want. Otherwise, the problem has no solution. Okay, so we've got this blind deconvolution problem, L plus S. We know nothing about the rank of L. We know nothing about S. We don't know how many entries have been corrupted, where they are, what their magnitude, what the magnitude of the corruption is, and so on and so forth. Okay, how do we do this? Convex programming. And here we do something which is connected to what we've seen just before for phase retrieval, we're going to try to find a solution, L hat and S hat, which are compatible with the measurements, so their sum must be what I've seen. And among all this decomposition, and of course there are infinitely many, I'm going to pick the one which minimizes a certain convex objective. I'm going to pick the nuclear norm for L, which is a sum of the singular values, so this is the equivalent of the trace when you're not positive semidefinite. Again, your proxy for the rank. And now we need to use a proxy for cardinality. And what is a proxy for cardinality? This is well known. We use the L1 norm. And so we have this very simple proposal where you minimize the nuclear norm plus a scalar times the 1 norm of S, subject to this. And this has been also proposed by the people I keep on mentioning. And I mean, it's deceptively simple. It's way too naive. All right, so here's our proposal. I get to see a low-rank matrix plus a sparse matrix. I solve this optimization problem, and the result is that this is actually completely exact. That is, when this program terminates, when I extract the solution of this convex optimization program, which is a semi-definite program, then I'm holding a guess L hat, which is exactly L, and S hat, which is exactly S. And this is completely parameter free. It is, how do you pick lambda here? 1 over square root of the dimension. That's it. So you have a matrix of almost full rank. You corrupt a constant fraction of the entries. So you have a situation that looks like this. You have many entries that are corrupted. You solve this optimization problem with lambda equals 1 over square root of n. And what the algorithm spits out is exactly L and exactly S. So if you make a low-rank matrix which is incoherent of almost full rank, and you start messing around entries that have been selected at random, then when you solve this optimization problem, you will actually see exactly which entries have been corrupted and how. All right. And what is a bit surprising from a statistical point of view is that this lambda is universal, like you don't look for it by cross-validation or stuff like this. All right, so now we're talking about something which is real, which is when you deploy this in the real world, you have phase transition, and these are real things. So when you look at, so on the x-axis, you see the rank of the low-rank component divided by n. On the y-axis, you see the fraction of corrupted entries. And then what we see is that if you see a gray pixel in this figure, is that it means that the algorithm succeeds 50% of the time and fails 50% of the time. And when you plot the probability of success, you don't see gray pixels. You see either white, you always work, or black, you always fail. And there's a very sharp transition between the two. And so if you're in the right region, for example, if you have a matrix of rank n over 10, what that plot says is that you can corrupt 30% of the entries with no harm whatsoever. And of course, as the rank diminishes, you can corrupt more and more. Of course, what you can do is you can say, well, what happens if you have missing information on top of it? So now we don't only have corruptions, but we also have a lot of missing samples. And maybe I'll skip this. I'll just say the result is exactly the same. When you get a lot of missing samples, what you just do is you change the value of lambda to be 1 over square root of the missing fraction times the dimension, and the low-rank component is exactly the same. So you have exact recovery, not only from corruption, but also from missing and corrupted data. Okay, so again, I mentioned some fun applications in background subtraction. So again, so if I give you a video sequence, we can think about L as a background and S as the sparse disturbance in the background. And so we've applied this to background subtraction with Emma and John Wright. So I'm going to show you a video which is not of our work. Our work is on YouTube if you'd like. I'm going to show you work from other researchers that confirm our findings. And so when you apply this convex model out of the box, you get something like this. So here you see the video sequence. Right. Here you see the low-rank component, which is the background, and the sparse component, which is this disturbance in this low-rank background, which are these people moving about this shopping mall, and so you do automatically background, foreground separation. Okay, so there are lots of applications in computer vision of these models and as these ideas, and in MR and many other fields as well, besides principal components. Okay, so we're done with story number 2, and my last story is about super resolution and his work with a fantastic graduate student at Stanford, Carlos Fernandez-Granda. So now we're going to switch field again, and that's the last time we switch field, so we're going to go back to optics, a slightly different kind of optics. And, well, as everyone knows, when you deal with an optical imaging system, we're going to have to deal with the laws of diffraction. And these laws say that if I'm interested in imaging a point source, and I take a picture, or I look at it through a telescope, or microscope, or whatever, this point source will not appear on the camera as a point source. Rather, it will be convolved with a transfer function, a point rate function, something that would look like this. Okay, and these are caused by the laws of diffraction. Even if you design a perfect system, this will be the output. Okay, so we cannot extract ourselves. I mean, the laws of diffraction are upon us. And what that means, it means that mathematically there is an object F that I'm interested in imaging, but I can only observe the convolution of F with a point spread function, which is essentially a low-pass object. In the Fourier domain, obviously this convolution becomes a product, and I'm getting to see the product of the transfer function with the spectrum of F. Now, in an optical system, typically you have a frequency cutoff, capital omega, and the transfer function is simply 0 after this cutoff. So there is no high frequency information about your object. The measurements have suppressed all the high frequency components, and if you open a book, a textbook in optics on page 1, you will see something like this. Well, in a coherent imaging system, what could be your transfer function? It will just be the indicator function of the pupil element, which, say, for example, is circular. The corresponding PSF is what people call an airy disk. And so what that means, it means that point sources will be convolved with this disk, and so they will appear to be fat. Okay. All right, so this is, of course, the basis for the limits of resolution as formalized by Lord Rayleigh. So we got our impulse, we got our response, transfer function, and what the Rayleigh distance is, precisely, it's the distance between the peak of your point spread function and the first zero crossing. This is what Rayleigh calls the Rayleigh distance. And other interpretation, of course, is if you take 2 point sources and you bring them close, it's the distance at which they will appear to be not 2, but just 1. Okay, that's our Rayleigh distance. Now, what is the super resolution problem? It's very simply stated. I've got low-pass information about a high-frequency object, something like looks like this, and I need to invert it. In the frequency domain, it takes a very simple following form, where you have the spectrum here of this object. I would like to see it everywhere, but I only see it in a low-pass band, and I need to extrapolate it. Now, I've seen a few sessions on compressed sensing at this conference. I want to say up front that it has nothing to do with compressed sensing, because in compressed sensing, one of the tenets is that you can actually sample the spectrum at will, at location that you can choose. In the super resolution problem, you can't. You only can see the low frequency because you're limited by diffraction. And so the compressive sensing from the get-go has always been an interpolation problem. Interpolate the spectrum in between the samples. The super resolution problem is very different. It's an extrapolation problem, so it looks much scarier. All right, so in this talk, we're going to be interested in resolving point sources. So for example, examples of point sources might be line spectra in spectral estimation or speech analysis. or they could be single molecules. And so we're working with a chemistry lab at Stanford, the lab of W.E. Murner, where we try to do single molecule imaging. And as you can guess, the problem is very simple. You see molecules, but these molecules are much smaller than the resolution of your microscope. They appear huge, and you want to beat the diffraction limit to localize them very precisely within the synapse. Okay, so the question is to beat the diffraction limit and super resolve the location of these molecules that appear to be, again, very fat, even though they're not. All right. So what is a model for story number 3? Well, I've got a superposition of point sources. Right? So I now have the real line, or maybe the interval, and I'm going to put point sources on this interval. And these point sources are at unknown locations, tau j, and have unknown, possibly complex amplitudes, aj. And now I have only low frequency information about these point sources. And so I'm going to model this by, well, what do I get to see? I get to see the Fourier transform, let's say a sample version of the Fourier transform, but at frequencies limited by a parameter that I'm going to call f low, the frequency cutoff. So I only see the spectrum until f low. And so because I don't have high frequency information from what we've seen, every physicist, everybody we know will tell you, well, okay, so you don't have frequencies, you don't see the spectrum beyond f low, so you can only think about a limit, a resolution limit, which is our Rayleigh distance, which is 1 over this frequency cutoff. And beyond that, you don't have any information, so you don't have the right to talk about resolution beyond this cutoff. Yet, what we're going to do is we're going to try to go beyond this resolution limit. And again, judging by looking at the program of this conference, there may be some of you working in wireless communications. So this is really, if I swap time and frequencies, it's a spectral estimation problem of trying to resolve frequencies from a few time samples of a signal by just swapping time and frequency. All right, so here's a problem. We have low frequency data. Looks like this. I've hidden spikes in here, so this is a convolution of a spike train with a sinc kernel. And where are the spikes? Well, it's not obvious. At least it's not obvious to me, but here they are. And that's what you need to do. You need to find them. All right, so now we're going to invoke convex programming a third time. And now we're going to do something which is even simpler than what we've seen before. We say, well, these spikes are anywhere. And so now the proposal is very simple. It says, well, I'm going to try to recover. So I have very few frequency samples at low frequencies. These are my linear constraints. I have, of course, many signals. It's continuous time now that are fitting these constraints. And among all of this, I'm going to try to find the one with minimum total variation norm. Okay, so what is a total variation norm? It's a norm that probabilists use to measure the distance between probability distributions. It simply is a continuous analog to the L1 norm. And so if I have a signal which is a superposition of amplitudes times spikes, the total variation norm will just be the sum of the amplitudes. So it really is a continuous analog to the L1 norm. Now, again, because of convex modeling, if you have noise, you would not enforce equality constraint, you would relax your constraint and minimize a trade-off between goodness of fit and small continuous L1 norm. Okay, so again, a very simple proposal that makes it doesn't know that we're looking for spikes. It doesn't know anything. It just finds a signal that has a minimum total variation norm and is compatible with these measurements. Okay, so we get very few frequency samples. And the result is something like this in this case. Is if the spikes are separated by twice the Rayleigh distance, then this program that knows nothing about nothing is just finding a signal with minimum L1 norm on the continuum. It knows nothing. It doesn't know we're looking for spikes. Then this program is actually returning the right answer perfectly. Right, so if the spikes are separated by twice the Rayleigh distance, then this optimization program will locate the spikes perfectly and recovers the amplitudes perfectly. It's a bit bizarre because we achieve infinite precision, which I can prove, but I still don't comprehend it. Why is it that the spikes are exactly where they should be and not jitter around the true location? I have no idea. That works whatever is the amplitudes. If the spikes are at twice the Rayleigh distance, you can actually bunch up a lot of them. Well, how many can you bunch up? If I get to see n, if I have n equations, n frequency samples, you can bunch them n over 4. So from the point of view of compressed sensing, it says that I can recover a k-sparse signal from just 4k measurements, provably. We have counterexamples with Carlos saying that if I try to bring them closer, L1 will fail. So if I try, you can make examples yourself on the computer, bring them closer, and if they are at the Rayleigh distance, L1 will fail. And I present you a result in 1D, but we have result in any dimension. The result is exactly the same. If you are essentially at twice the Rayleigh distance, in 2D, 3D, whatever, you have a perfect localization. Okay, so there is this separation condition, which is new, which you do not see in compressed sensing. And the reason you don't see it in compressed sensing is, well, in compressed sensing, you sample the spectrum at random. In super resolution, you do not. You just see the low frequency part. And so here are a bunch of very sparse signal, a bunch of spikes, except they're very close to each other. And then on the right, you see the spectrum. And the blue portion here is the portion you get to see. And so essentially, this signal has zero energy on the low frequencies. And so if the spikes are close together, maybe algebraically you can recover them, but you would need 300 dB to do this. On the other hand, if I take the same signal and I start to spread them a bit more, beyond the Rayleigh distance, then the spectrum gets narrower. Now I see the low frequencies. Now there's a lot of energy and I can work. And I can actually have stability. Now I don't want to dwell too much on this, but there's a true giant in this field that understands this better than everybody else, and that's David Slepian. David Slepian, through his monumental work on Prolate's Fördel function, is able to tell you that if the distance between the spikes is below the Rayleigh distance, you cannot hope for any stability. The problem is completely ill-posed. And what we're showing here is that if the problem is, if the spikes are slightly above the Rayleigh distance, then you can solve it by convex programming. Okay, so it's going to be time to wrap up. What we have is we have a story with noise. And with noise, maybe I'll just say what the story says is, well, you get low-pass data, so you have a microscope, a telescope, and the telescope has a certain aperture. And, you know, if you look at the physicists going to NSF, they will say, government, we need to build a bigger telescope to increase resolution, to fit our cosmological model better. Right? So a telescope has a certain PSF with a certain width. They want to build a bigger microscope, which is something like this. The question is, can you do it without building the telescope? That's the subject of super resolution. And what we use is we use this kind of metaphor to say, this is a resolution at which you have data. There's a resolution you wish for. And when you have noise, what will be the mean squared error in terms of this ratio between the resolution at which you have data and your resolution target? So I'll skip this. In the interest of time, I will not show this. Okay. So now we've got this, and that's kind of my last slide. We got this optimization problem, which is taking place on the continuum. So how on earth are we going to solve this optimization problem? Now, I have to recover a continuous time signal. How on earth are we going to solve it? Well, I claim that, again, it's a semi-definite program, and it's the last semi-definite program we will ever see in this lecture. So now I've got an object I'm looking for, which is continuous time, so it's infinite dimensional. And like every convex program has a dual, and what is its dual? Well, what I need to do on the dual formulation is I need to find a coefficient vector C, which is finite dimensional, In fact, its length is just the number of equations I've got. So it's finite dimensional. I need to be able to maximize this dot product subject to these infinity constraints. So what is a dual variable C? These are the coefficients of a trigonometric polynomial. And what is a dual program telling me? It says, please maximize this dot product between the data and those coefficients C under the constraint that this trigonometric polynomial be bounded by 1 over the line. All right, fine. But now we've not really advanced anything because, well, maybe I have a finite number of variables, but I have infinitely many constraints. So conservation of difficulty. It turns out that maybe some of you know that this is semi-definite program, SDP representable. Checking having coefficients C such that the trigonometric polynomial is less than 1 can be cast as a semi-definite program. And that's what people know in control, more or less, or in system theory. That kind of is related to the Kalman Y, and I forgot the last name, theorem. Checking, there are coefficients C, this trigonometric polynomial will be less than 1 if and only if there's a symmetric matrix Q such that this matrix is positive semi-definite and Q has trace 1, and then when I sum Q along superdiagonals, they vanish. So it's interesting for us. And why is it interesting for us? Well, because now I can solve the dual instead, which is a semi-definite program, so I know how to do this. Oops. All right, so I look at the dual, I solve it, and I get coefficient C. And what do I do with them? Well, it's simple. I get a trigonometric polynomial, right, with coefficient C. I check when this trigonometric polynomial takes the value plus or minus 1. This is exactly where the signal is not 0. And so I recover the location of the spikes. So to recover the spike location, solve the dual problem, check when this trigonometric polynomial takes the value 1. This is exactly where the spikes are. All right, an example. Here are some noisy measurements about a spike train. In fact, the true measurements, if I had no noise, would look like something like this. So I have about 14 dB error. Okay. The true spikes are somewhere here. And I solve this semi-definite program, check where the thing takes the value plus or minus 1. And what I get is I recover these spikes perfect. Well, not perfectly, because now there's noise. If we did noiseless, it would be silly, because you would say an accuracy of 10 to minus 10. We have a bit of noise, so you recover up to 3 digits of accuracy, the location of this thing. Okay, so my time is up. I decided to talk about 3 stories. Phase retrieval, matrix completion, or RPCA super resolution. I think what's nice about these techniques is that they work well, both in theory and in practice. They're model-free. Like, you don't make any modeling assumptions when you use these methods. And yet they give near-perfect solutions in parametric setups. I committed a big crime, which is I did not talk about algorithm. I did not talk a lot about applications. And I did not mention an avalanche of related works. And so I will just leave you with a bunch of papers from other people related to these topics that I've enjoyed enormously. And so, for example, I take the first one. The first one, we're very lucky at Stanford about a few weeks ago to receive the visit of Netrapalli and Jain, who present phenomenal work on phase retrieval, not using convex programming IDs, but using alternative minimization. And so I encourage you to check this literature, and I thank you for your time.
Thank you, Emmanuel, for an amazing talk. It's taught me that in the future, when people tell me that a problem can't be solved, I should be very suspicious and wait until Emmanuel actually agrees. We have time for maybe one question at most, because we are running on a tight schedule. Would anybody like to ask a question? I can't actually. Okay. Well, Emmanuel, thank you so much again.